Hello, today's date is November 28th, 2016. My name is Jacob Wood, and the purpose of this video is to accomplish the analog circuit achievement for the Oregon State EECS Mastery Challenge. For the first portion of this video, I will be focusing on demonstrating the use of diodes within a circuit, and to model the functionality of these different components, I will be using my ECE 322 power supply. It's pretty messy with all these jumpers. But for the first portion of this video, I'll be focusing on these diodes here, 4 diodes, and these make up the full wave bridge rectification block of this system. And you can see this subcircuit here with the 4 diodes in the middle there. And the purpose of this rectification is to take an alternating input here, and we step it down with this 5-to-1 transformer. And ideally we want to take this large alternating input and break it up into a pulsing positive output and negative output. So how this works is we take the alternating input here, and these diodes here have about a 0.7 voltage threshold, and this diode here will allow positive portions of this. So basically the half cycle, the positive portion of the alternating circuit or input will come up here to this V positive node, and negative portions of this input will be allowed by this diode, as this potential will be lower than here, and the negative half cycles will be pushed to this V negative node. Same for this inverting portion of the input. Positive portions will go up to this V positive node and negative to this V negative node. Next, I will be demonstrating the use of an NMOS within this circuit, our voltage supply. So here, connected to the rectifier circuit, you can see this MOSFET. It's an NMOS here on the right. The purpose of this MOSFET-oriented subcircuit was to drain the large capacitors used as smoothing from the split portions of the rectifier block. So this MOSFET over here on the right acts like a switch. So it's in cutoff mode while the supply is on. And when the supply is off, this voltage at the gate of this MOSFET goes from about negative 16 volts to 0, and will actually switch this MOSFET into a saturation region. When this happens, the current will be able to flow through this MOSFET, and we chose these resistor and capacitance values to determine a sufficient amount of time that these capacitors will be drained in. So you can see how this would work, where this LED shows when the supply is on and how quickly it drains. Next, I will be demonstrating the use of BJTs within this circuit. So you might be able to see them here. Unfortunately, it's a little unclear with all the jumper wire, but this heat-sinked BJT, and maybe you can see all these other darker BJTs, but this subcircuit is a voltage regulator. You can see a schematic here. The purpose of this circuit was to basically set the output voltage and maintain that, and do some current limiting to protect some of these components. So basically what controls this output voltage is this V out here is this R3, which was a variable resistor, is a 100K potentiometer, and when it is at its highest, the lowest amount of voltage is seen at this node, the base of Q3, and this allows the most current to pass through here into our output voltage. This goes, when this voltage increases and this resistance therefore is minimal, we have more current sinking through this transistor and less out to V out, which represents our lower end of our voltage supply. Lastly, I will be demonstrating the use of OPAMPS, feedback, and temperature control within this power supply circuit. So if we zoom in here, you can see that fan up there. In the center of this screen capture, you might be able to see our op-amp chip, and directly to the left of that is the thermistor. You can see the schematic of this circuit here, and you can see the op-amp in the center there, and the negative feedback, which is tied to the inverting node of the op-amp and the output of the op-amp. And how this circuit works is you see this thermistor here. When the ambient temperature of this thermistor increases, its resistance decreases. This will decrease the voltage at this inverting node, which this op-amp will then try to drive this output voltage higher, which will increase the current through this resistor, increasing the current in at the base of this BJT, and effectively this will increase the current through this top node as well. And increasing the current to this top node will then speed up the fan. So we can demonstrate this. We turn our power supply on and we touch this thermistor. We should be able to heat it up to the point where our fan will begin. And our fan starts there.